Alright, good everyone. So you are welcome to this week's class of HPHY404. So today we'll review complex numbers. So a complex number denoted as Z has a real part of the complex number plus the imaginary part of the complex number. So usually we write Z equals X plus IY, where this X is the real part. So X is the real part of Z and Y is the imaginary part of Z. So if you have a number Z equals 2 plus 3I, so this is a complex number because there is both the real part and the imaginary part. The real part here is 2, while the imaginary part here is 3. Okay, so a complex number has a real part and an imaginary part. So the imaginary part has this complex term I. So this I means the square root of minus 1. The square root of minus 1. For example, if you try to solve this quadratic equation, z squared minus 4z plus 5 equals 0. So if you try to solve this using maybe the formula method, so at the end of the day you get z equals 2 plus or minus square root of minus 4 divided by 2. Okay, so you can use the formula method. Okay, you have minus b plus or minus square root of b squared minus 4ac everything divided by 2a. So in this case, a is 1, b is minus 4, and c is 5. Now, if you get this, you have this square root of minus 4. Square root of minus 4 is not 2. So this square root of minus 4 can be written as square root of minus 1, then multiplied by square root of 4. So this square root of minus 1 is the complex part. So, and it is denoted as I. So we can just write, square root of 4 is 2. We can just write this as 2I. So where this I is square root of minus 1. So in this particular problem, we can write it as 2 plus or minus 2I over 2, or 2 plus or minus I. Okay, so in this case there are two solutions. So the first solution Z1 is 2 plus I, and the second solution Z2 is 2 minus I. So in this case the real part is 2, so 2 is the real, and the imaginary part is 1. Okay, so the real part here, real part of Z1 is 2, imaginary part of Z1 is 1. Whereas in this case the real part of Z2 is 2, while the imaginary part of Z2 is minus 1. Okay, so I believe that should be understood now. So in compact form, you can write a complex number. You know, we wrote it here as x plus iy. X plus iy. So you can write it, instead of x plus iy, you can just write in compact form as x comma y. Now, we can plot a complex number on an Gantt diagram. Okay, so we plot the we plot the real part on the horizontal axis, and we plot the imaginary part on the vertical axis. Okay, for example, let's say we want to plot z equals maybe 3 plus 2i. So 3 is the real part, so it will be plotted on the horizontal axis. So let's say this is 1, this is 2, and this is 3, and this is 4, and this is 1, 2, 3, 4, and so on. So this x, which is 3, that's the real part. So the real part is 3, okay, and the imaginary part is 2, so 2. So the z is here. So z, which is 3, 2, that is 3 plus 2i. Okay, 3, the real part is 3, and the imaginary part is 2. So this is how you plot this complex number. So you plot the real part on the horizontal axis and you plot the imaginary part on the vertical axis. Then, how do we add complex numbers? Okay, so let me say addition and subtraction of complex numbers. Okay, so if you have a complex number z, let's say z1, in general plus or minus z2, whether it is z1 plus z2 or z1 minus z2. So if it is z1 plus z2, then it will be x1. Okay, before that, let me explain what I mean by z1. So let's say z1 is x1 plus I y1. So the real part of z1 is x1. The imaginary part of z1 is y1. And we have z2, which is also x2 plus I y2. Then if you want to add or subtract z1 and z2, then it's going to be you add the real part or subtract the real part, then you add it to the imaginary part. So again, the imaginary part will also be y plus or minus y2. So if it is addition, then you choose x1 plus x2 plus I into bracket y1 plus y2. And if it is subtraction, if it is z1 minus z2, you choose x1 minus x2 plus I into bracket y1 minus y2. For example, so let's say z1 is 3 plus 2i and z2 is maybe minus 6 plus 3i, something like that. So in this case, z1 is 3. So z1 is 3. The real part of z1 is 3. The imaginary part of z1 is 2. Real part of z2 is minus 6. And the imaginary part of z2 is 3. So if you want to add z1 and z2 in this case, then it's just going to be the real part. This is the real part. Okay, real part. That will be 3 minus 6. That will be minus 3. Then plus I, the imaginary part. The imaginary part is 2 plus 3. So that will be 5i. Okay. Then if you want to do z1 minus z2, then it's going to be 3 minus 6. That will be 3 plus 6. Okay, because the real part here is 3. The real part here is minus 6. So if you want to subtract minus 6 from 3, it will be 3 minus 6. That will be 3 plus 6, and that will be 9. Then the imaginary part, so plus I into back. The imaginary part you subtract as well, so 2 minus 3, that will be minus 1. Then you can write this as 9 minus I. So the real part is the addition of z1 and z2 is minus 3 plus 5i, and the subtraction of z1 and z2 is 9 minus I. So what all you need to do is add the real part if it is addition, add the imaginary part if it's addition. For subtraction, subtract the imaginary parts, then subtract the real part. Okay? So next, modulus and arguments. So modulus and arguments. Now I plotted this Argand diagram. So let me plot the Argand diagram again. So let's say we have, so this is the real part of z, and this is the imaginary part of z. So let's say the real part is x and the imaginary part is y. So if you plot the graph on the Argand diagram, sorry. Okay, so this will be z, this point, which is x comma y. So x is the real part and y is the imaginary part. Now if you draw a line from the origin, okay, 0 0 up to the points z, x comma y, that line denotes the modulus of the complex number. Denotes the modulus of the complex number. So the modulus, we denote it as this, okay, modulus of z. And if you want to obtain the modulus of z, you find the square root of the square of the real part plus the square of the imaginary part. So that is how you find the modulus of a complex number. Now, what about the argument? So the argument is this angle. So this is the argument of z. Argument of z, this angle. So if you want to find the argument of the complex number, it is arctan of the imaginary part divided by the real part. Okay, the imaginary part, that is the imaginary part of the complex number, divided by the real part of the complex number. So the real part is denoted as x, while the imaginary part is denoted as y. So this is how you calculate modulus and argument of the complex number. Okay, so let's take a quick example. So for example, so given that z, the complex number, equals 2 minus 3i. So if you want to find the modulus, so the modulus of z will be square root of the real part is 2, so 2 squared, plus the imaginary part is minus 3, so minus 3 squared. So and this will be square of 2 is 4, square of minus 3 is 9. So 9 plus 4, that is 13. So that will be square root of 13. So that is the modulus of this complex number, 2 minus 3i. What about the argument of the complex number? So the argument we said is arctan of the real part, arctan of the imaginary part divided by the real part. The imaginary part here is minus 3, and the real part here is 2. So if you find this arctan on the calculator, alright, so if we take out our calculator and find the arctan of minus 3 over 2, so we get minus 56.3099. Okay, so this is minus 56.3099 degrees. Okay, that will be the argument of z. So it means this angle, so it means if you plot this is the real part and this is the imaginary part. So if you plot 2 comma minus 3, okay, sorry, so here we have a negative imaginary part. So this is the real z, imaginary z, and the negative axis of imaginary part of z. So if let's say this is minus 1, minus 2, minus 3, minus 4. So you have minus 1, minus 2, minus 3, minus 4. This is 1, 2, 3, and so on. So this is 1, 2, 3, 4, minus 1, and so on. So here the real part of z is 2. So 2 here. And the imaginary part is minus 3. So this is minus 3. And this is 2. So the point is here. Okay. Now this is the modulus. And the modulus is square root of 13. And the argument is this argument here. So it is minus 53, so 56.3099. So this is the argument here. Alright. So next is multiplication. Multiplication of two complex numbers. So again, so we denoted z1 as x1 plus i1, z2 as x2 plus iy2. So if we want to multiply those two complex numbers, z1 and z2, so we have z1, z2, so it will be z1 is x1 plus iy1, while z2 is what? x2 plus iy2. So if you multiply, so x1 multiplied by x2 plus x1 multiplied by iy2 plus iy1 multiplied by x2 plus iy1 multiplied by iy2. So if you do the multiplication, at the end of the day you have x1, x2 minus y1, y2 plus I, x1, y2 plus y1 x2. Okay, now for example, so let's say you have z1 equals 3 plus 2i, and you have z2 equals minus 1 minus 4i, and you want to find the multiplication of z1 and z2. So then it will be 3 plus 2i minus 1 minus 4i. So the way you do normal multiplication, expansion of the brackets. So you have 3 multiplied by minus 1, that will be minus 3. 3 multiplied by 4 minus 4i, that will be minus 12i. Then 2i multiplied by minus 1, that will be minus 2i. Then plus times minus is minus, but I multiplied by I is also minus, so that will make it plus. Then 2 times 4, 8. So what I've done here, I've multiplied 2i by minus 4i. So plus multiplied by minus is minus, but I multiplied by I, because I is square root of minus 1. So I squared is minus 1. Okay, so I squared is minus 1. So that will make this to be plus. Then 2 times 4, 8. So this will now be minus 3 plus 8, that will be 5. Then minus 12i minus 2i, that will be minus 14i. So this will be the result of the product of these two complex numbers. z1 equals 3 plus 2i, and z2 equals minus 1 minus 4i. Alright, now you should note that the multiplication of complex numbers is both commutative and associative. Okay, so what do we mean by commutative? Commutative means that if you find the product of z1 and z2, it is the same as finding z2 multiplied by z1. It's the same. So this is commutative. What about associative? So that is whether we find, in this case, whether we put 3 plus 2i first, minus 1 minus 4i second, or we put minus 1 minus 4i multiplied by 3 plus 2i. We're going to get the same answer of 5 minus 4i. We're going to get the same thing. So that is what we mean by commutative. So whether you put the z1 first or you put the z2 first, so you get the same results. What about associative? Associative means that if you first multiply z1 by z2, then you multiply the result by z3. It is the same as first multiplying z2 and z3, then multiplying the result by what? z1. So this is what we mean by associative. Okay, so they are the same. Also, if you find the modulus of the product of z1 and z2, it is the same as finding the modulus of z1, then multiplying the result by the modulus of z2. So you should take note of this with the argument as well. So the argument of z1 multiplied by z2 is the same as the argument of z1 plus the argument of z2. Okay, so let's take a simple example. So let's say verify that the commutative claim, holds. So verify that z1 z2 equals z1 modulo z1 modulo z2 holds for the product of so let's say z1 is still 3 plus 2i. I think we have used 3 plus 2a, okay, and z2 equals minus 1 minus 4i, minus 1 minus 4i. Okay, now So we want to verify if this claim holds. Okay, using this z1 equals 3 plus 2i, z2 equals minus 1 minus 4i. Now, we have already found the product of z1, z2. We got 5 minus 14i. Okay, so the modulus of z1, z2, we already found z1, z2. So it means it will be the modulus of z1, z2 is 5 minus 14i. So of 5 minus 14i. So the modulus of 5 minus 14i means the square root of 5 squared plus the square root of minus 14 squared. And that will give the square root of 221. Now, if you find the modulus of z1, z1 is 3 plus 2i. So the modulus will be 3 squared, which is 9, plus 2 squared, which is 4. So that will be square root of 13. Also, if you find the modulus of z2, it will be square root of minus 1 squared, which is 1, plus square root of 4 squared, which is 16. 16 plus 1 is 17. Now, if you find the product of z1 and z2, the modulus of z1 and z2, then it will be square root of 13 multiplied by square root of 17, which will be square root of 13 multiplied by 17, and that will give us the square root of 221. Okay, so square root of 221 here, square root of 221 here. So therefore, the claim that the modulus of z1, z2 equals the modulus of z1 multiplied by the modulus of z2 is valid, or is true. Okay, or is verified. Okay, all right. So next is complex conjugates. Complex conjugates. Complex conjugates. All right. So what is complex conjugate? So if we denote our complex number z as x plus iy, the real part is x, the imaginary part is y. Okay. Now the complex conjugate of z, we often denote it as either z star, z asterisks, or z bar. Okay, so I think I'm going to use z asterisks equals. So what you do is you change the sign of the imaginary part. So the sign of the imaginary part is positive here, so you change it to negative. So it will be x minus iy. Okay, so the complex conjugate of z is x minus iy. So actually the complex conjugation it corresponds to a reflection of the complex number in the real axis of the Argand diagram. What do I mean? So if you plot a graph of the real part of z against the imaginary part, so this is the imaginary part positive aspect, the imaginary part the negative axis. Okay, if you do this, so minus imaginary, so let's just choose arbitrary points. This is x, this is y, and if you plot, so this will be z, which is x plus iy. Now the reflection of this complex number in the real axis, okay, corresponds to, so the mirror in the real axis of this will correspond to this minus y. Okay, so this is now z asterisk equals x minus iy. Okay, so this is the modulus of z, and this is the modulus of z asterisk. Okay, modulus of z and modulus of z asterisk. All right, so the complex conjugate means you change the sign of the imaginary part. If it is positive, you change it to negative. If it's negative, you change it to positive. For example, if you have z equals 3 plus 6i, then the complex conjugate is going to be 3 minus 6i. And if you have complex number of minus 2 minus 3i, the complex conjugate will be minus 2 plus 3i. You change the sign of only the imaginary part. Okay, and you can have z to be maybe minus 4i, then z, the complex conjugate, is 4i. What if you have z to be 6? What do you think will be the imaginary part? Can you guess? The complex conjugate. Z is 6. What will be the complex conjugate? It is still 6, because this is just the real part. Okay, so the conjugation, the complex conjugation, affects only the imaginary part. Okay, please take note of that. Okay, then you should note that if you find the complex conjugate of z1 plus or minus z2, it is the same as finding the complex conjugate of z1 plus or minus the complex conjugate of z2. Similarly, the product of z1 and z2, the complex conjugate, is the same thing as finding the complex conjugate of z1, then multiply it by the complex conjugate of z2. So also, the division of z1 by z2, the complex conjugate, gives the complex conjugate of z1 divided by the complex conjugate of z2. We'll look at division of complex numbers shortly. All right. So what if you are given? So what the question says: find the complex conjugate of. So let's say we have z equals w raised to the power of 3y plus 2ix, where w equals x plus 5i. Okay, so what will be the complex conjugate? So the complex conjugate will be w is x plus 5i. Okay, so the complex conjugate of this part is going to be x minus 5i. Okay, then the power will be 3y minus 2ix. Okay, minus 3. So that will be the complex conjugate of the given complex number. So you should also note that the following properties, of complex conjugates can be easily proved. So you should try as much as possible to prove these relations. So if you find the complex conjugate of a number and you find the complex conjugate again, it will give you the actual complex number of a complex number. For example, let me do this first one. So if you have z equals 2 plus 3i, so if you find the complex conjugate, it's going to be 2 minus 3i. If you find the complex conjugate of that again, it will be 2 plus 3i. So back to the original complex number. So z, the complex conjugate of another complex conjugate, is just the complex number. So the remaining relations are the addition of z and z star is twice 2 of the real part of z, which is 2x. The real part is x, the imaginary part is y. So similarly, z minus z star is 2i, then the imaginary part of z, which is 2iy. Sorry, this is asterisks. So the same thing with the division, z over z asterisks, so equals x squared minus y squared divided by x squared plus y squared plus I 2xy over x squared plus y squared. All right, so let's look at division here. Division. So if you have two complex numbers, z1 and z2, and you want to divide z1 by z2, okay, so z1 is x1 plus I y1, and z2 is x2 plus I y2. Okay, so what you do is you multiply both the numerator and the denominator by the complex conjugate of the denominator. Okay, by the complex conjugate of the denominator. Now the complex conjugate of the denominator is, so let me put this in brackets, is x2 minus I y2. x2 minus I y2. So, and if you do that, at the end of the day, you obtain x1, x2 plus y1, y2 divided by x2 squared plus y2 squared plus I x2 y1 minus x1 y2 divided by this same value, x2 squared plus y2 squared. Okay, now let's take this just short simple example here. So the simple question says express z in the form x plus I y when we are given z to be 3 minus 2i divided by minus 1 plus 4i. Okay, so what you do is you 3 minus 2i minus 1 plus 4i. So you multiply both the numerator and denominator by the complex conjugate of the denominator. So that will be minus 1 minus 4i. Minus 1 minus 4i. Okay, so if you multiply this, 3 multiplied by minus 1, that will be minus 3. 3 multiplied by minus 4i, minus 12i. Minus 2i multiplied by minus 1, that will be plus 2i. Then minus times minus is plus, but I times I is minus, so that will be minus 2 times 4 is 8. Then divided by minus 1 times minus 1, 1. Minus 1 multiplied by minus 4 plus 4i plus 4i multiplied by minus 1, that will be minus 4i. Then plus times minus is minus 4i times 4i, that will be minus 4 squared, which is 16. So this will be plus 16. So at the end of the day, this will be minus 3 minus 8, that will be minus 11. Minus 12i plus 2i, that will be minus 10i. Then divided by 4i minus 4i, 0. 1 plus 16, that will be 17. So that z can now be written, so z is minus 11 minus 10i over 17. Or we can write it as minus 11 over 17 minus 10 over 17i. So I think we'll stop here for today because it's getting long. So we'll stop here for today, and next time we'll continue from where we stop. All right, so see you next time. Bye bye.